Today we're at Compass Barron Quarry. We're doing some training, doing topographic surveys and orthomosaics with construction drone services, which is Ian, Chris and myself, Dave, and we all represent different drone companies. This is a collaborative effort that we're doing, combining our skills in different parts of the kind of workflow in producing orthomosaics. So today we're out doing just a practice run using a new base station and doing some workflow efficiency improvement, I guess, using these ground control points, the Inspire 2, and I believe we're using Pix4D for mission planning today to create the orthomosaic of this quarry face behind us. We'll also be doing some processing of the imagery afterwards and looking at the kind of relative accuracies we're achieving, doing some actual physical measurements of targets on the ground to see how they look and compare in the actual software afterwards versus what we've ground truthed on the ground.
The first part of planning an aerial survey, we follow a set of steps that we have in an operations manual. The first part is usually looking for any nearby air hazards such as airports and other restricted areas such as power stations, prisons, that sort of thing. Should we find we do have an airport in the vicinity, it doesn't necessarily mean that we can't undertake a drone operation. It just means that there's a little bit more work involved in getting permissions from the airport and working with them to see if we can authorise a safe flight. Once we have determined that there aren't any immediate risks in air traffic, we would then do an on-site survey and look at areas such as local habitation, local properties, farms, any other hazards that may be a problem. Our next step would be to program an automated mission using software such as Pix4D Capture or Drone Deploy. This would just make sure that we had the right number of photos taken at the correct interval to ensure that there's a correct overlap to perform photogrammetry. On site, we would proceed to set up a series of ground control points around the site. There would typically be 5 to 10 of these scattered around the area which we would be doing the survey of. The idea of these is that they would give a fixed point in the ground which we could correlate with the images we were taking to georeference the photography correctly. These would be taken using survey equipment, so they'd be, in this case here we're using a base station and a survey pole, and using a post-processing method to achieve this. We then go about setting up the mission and the drone hardware to undertake the mission. In this case we're using Pix4D Capture, so we then proceed to power everything up and push that mission to the drone ready for an automated flight. Using this automated software, the drone would have a series of waypoints loaded up and it would proceed to perform the mission automatically and capture a number of photographs at a set position and height. As part of our CAA PFCO, we still have to have manual control over it should there be any sort of aircraft incursion. And also as part of that we have a competent observer which would be accompanying the pilot in case of any sort of airspace infringement. After the mission is complete, the drone would return to its set home point and automatically land. After the mission is complete, we would then remove all our gear from the site and take the imagery off-site to post-process. Back at the office, we've now downloaded the log files from the base and rover station and processed them using a software called RTKlib. This is used in conjunction with correction observations from a local base station. In the UK these are usually run by the Ordnance Survey. They provide RINEX files with atmospheric correction information which we use in conjunction with our own to derive a more accurate position. Moving on to the photogrammetry operation with Pix4D Mapper. I've already run this project, but in the case we have here, I'll just chat about it from the start. Once we have imported all our photography into Pix4D, it gives us this overview whereby it's downloaded the geotags from each photograph taken from the drone, and this shows a good example of verifying the flight path is what we would have expected it to be. Here we see a more defined cluster where Chris, who was flying this day, flew manually to get oblique images of the quarry face to improve the 3D model. Now this would typically run for a couple of hours, and the results would be the point cloud and various other derivatives that we'd get from the photogrammetry operation in Pix4D. So here again is a quick verification. In this case we're using a multi-rotor, so we expect all the images to be looking straight down because it has a gimbal. In some cases, doing larger mapping operations with a fixed wing, these might well be tilted a little bit to the right or the left, depending on which direction the aircraft was flying to the wind. That would typically be for a fixed wing drone that looks like a miniature aeroplane. So if I remove the cameras, we can get a better look at the point cloud. This would be typically something similar to what you would see with LiDAR. In the case of LiDAR, each of these points would be a single laser bounce between the aircraft sensor and the ground. But in the case of photogrammetry, what we see here is each of these points is actually a matching key point between two photographs taken from the drone, and this is in essence how photogrammetry works in building up 3D information by comparing 2 points in images which have a set position apart, and we also have technical information on the camera such as its focal length to get some sort of bearing on the distance that the camera is from an object. Pix4D comes with a handy little module where we can classify our point cloud. This is a big advantage when it comes to making an actual contour map, because things like here, like trees, we would call the actual terrain model, such as high grass and trees, and we're not necessarily interested in that. We want to look at the surface. So Pix4D has this kind of module to be able to remove some of these points in the point cloud to give us as clean a contour map as possible. Finally, one thing I thought I would show here is that for 3D modelling, Pix4D can combine all this information from the depth of the point cloud points and also the images taken from the camera to make a 3D mesh. These type of things can be of interest to kind of a variety of stakeholders. We've had quite a few inquiries of people wanting to look at positions where they might build a house or property and wanted a kind of 3D model to kind of view the area where their future home might sit, or a building for that matter. But the possibilities of this are endless. With a model like this, once it's imported into a 3D games engine such as Unity, with a model like this can typically be imported into a 3D software or a games engine where you can have a small character rig which would be able to, you would give you a point of view perspective from within the model which you could walk around with say virtual reality specs or some other type of viewer. So one of the ways that one of the outputs that we were looking for in this project was our topographical map. Pix4D is primarily a processing software. It doesn't have a great amount of tools for visualization or for measurement. When Pix4D completes, depending on what our processing objectives were, it can output a number of files, such as our digital surface model, terrain models, and one thing we're looking for here was contours. So we can now go and take a look at that. Here we see the hillside behind the quarry face and the steeper contours as the quarry face and the scree slope down into the quarry. This was a quick demonstration of a relatively small area, but in the future we'll be adding to this series looking at much larger models over several square miles.